came up with a form almost all physical problems that we will encounter in this particular course will be satisfying this type of governing differential equation. Of course, if it is a one dimensional problem it will eventually boil down to an ordinary differential equation, but for a general problem the prototype governing equation will be of essentially this type. So, it is important for us to get a feel of the particular characteristics or special features of these types of equations, so that we can make an assessment of the kind of numerical method that should be applicable for solving them, because depending on the nature of the partial differential equation one has to design suitable numerical strategies. It is not that in this generic form you have a unique simulation strategy or unique numerical solution strategy. It all depends on what is the particular type of the partial differential equation, and to understand that of course we can get into the broad theory of partial differential equations, but we will not try to do that. We will try to get into only some aspects of the theory of the partial differential equations which broadly can cover equations of this prototype. So, you can understand that these equations are second order partial differential equations. Why? Where does the second order term come from? It comes from the diffusion term. So, because it is a second order partial differential equation we will try to start or begin with a prototype form of the second order partial differential equation. Let us say that we have a partial differential equation of this type, where the notations are like this: phi x means del phi del x, phi y means del phi del y, phi x x means del square phi del x square, phi x y means and phi y y means this. So, these are just shorthand notations for writing the different partial derivatives. So, this contains a maximum up to second order partial derivative, that is why this is a second order partial differential equation, and we have retained all possible functional dependencies. Remember this a, b, c, d, these are not constants in general, these could be functions of other variables. So, we can sort of split it into two types of terms. One type of term contains the highest order partial derivative which is the first three terms, and these terms contain the either the function or the lower order partial derivatives or the independent variables. So, the solution what you expect is that what is phi as a function of x y, function of two variables. Now, let us see that how do we go about it. To do that, let us first try to understand that what can be different types of these partial differential equations. Now, the classification may be of different types. One type of classification is by classifying it in terms of linear or non-linear. So, when you say it is a linear partial differential equation, what do we mean? You have A, B, C, these are functions of x, y only. And the remaining term which are there, these are supposed to be linear functions of phi, phi x, phi y, like that. So, there is no non-linearity involved. If this is not satisfied, we say that it is a non-linear equation, but there are special types of non-linear partial differential equations which are called as quasi-linear, where this A, B, C, these are functions of x, y, but also u, ux, uy, or here it is phi, phi, phi x, phi y. Now, what we will do with this classification? It is of course important to note whether the equation is linear or quasi linear or non-linear. In general, I mean quasi linear is a special type of non-linear, but you could have other types of non-linear equations, and it is important to know this because the solution strategy will depend on which type of equation is it. And not only that, once you have a type of equation, you can attach with that or associate with that a particular physical perspective. For example, many of the equations in fluid dynamics will be quasi linear in nature. So, for example, if you have a term of this type u del u del x, so you can see that you could have a non-linearity because of a multiplication of u with a differential function of u. So, you could have a nonlinear differential equation which describes the fluid flow. So, when we will be describing the fluid flow equations in details, we will see that this nonlinearity is one of the key aspects of the Navier-Stokes equations, and how to take that into account while solving the Navier-Stokes equations is one of the big challenges. To proceed further, what we will do is we will identify certain aspects known as characteristics of the partial differential equations. The first question that we would like to answer is, what is a characteristic? Now, when you say this partial differential equation, it involves with it the partial derivatives, and there are highest order partial derivatives like phi xx, phi xy, phi yy, like that. These are the highest order partial derivatives appearing in a second order partial differential equation. So, when you have these partial derivatives, these partial derivatives may be continuous or may be discontinuous over some portion of the domain. You may not ensure that trivially the partial derivatives are continuous at all points. So, there may be locations or there may be lines, certain lines across which the partial derivatives may be discontinuous, and these lines are called as characteristics of the partial differential equations. So, why these are lines? Because you have the domain xy as maybe a plane. So, on that domain you could have certain lines across which you could have discontinuities in the derivatives, in the highest order derivatives of the variable phi, and those are called as characteristic lines. So, characteristics of the partial differential equation with reference to the second order partial differential equations are lines across which you could have discontinuities in the highest order derivatives, here second order derivatives. Why it is important to understand or identify? See, if there are discontinuities in certain variables, your numerical method that you are using should be able to accommodate that discontinuity. So, if you do not know a priori whether there will be discontinuity or not, you cannot design the numerical method. So, looking at the partial differential equation, you must first ascertain whether such discontinuities exist or not. If such discontinuities may exist, then your numerical method should take care of, should be capable of taking care of such discontinuities. How do we assess whether such discontinuities are there? So, to do that, what we will do is, since the highest order partial derivatives are the important parameters, we will club all other terms in the form of a function called as h, just we give a name of this as h, and then proceed further in mathematical simplification. First, what we do is we write phi x and phi y as functions of what? X and y, these are functions of x and y. So, from here you can write d of phi x okay. Similarly, phi y is a function of x and y. So, d phi y is this one. Since phi yx and phi xy are the same, the order of the derivative so long as it exists does not matter. So, we can write this also as phi xy. So, let us try to organize these equations. We have now got these 3 equations 1, 2 and 3. We want to organize these equations with an objective that we are interested to get the characteristics of the partial differential equation. So, we arrange this in a matrix form. So, from the equation 1, it is a into phi xx plus b into phi xy plus c into phi yy is equal to minus h. From the second equation, phi xx into dx plus phi xy into dy, there is no phi yy, is equal to d phi x. And the third one, this is 0, phi xy into dx and this into dy is equal to d phi y. Why have we arranged it in this particular form? Because we are interested in the variables in the highest order derivatives. So, phi xx, phi xy, phi yy, these are the variables for which we are interested. Along the characteristic lines, these will be discontinuous. So, we are interested about the values of these variables. So, as if it is a pseudo linear algebraic form Ax equal to b, where A is this matrix, x is this one and b is this one. We are interested about the case when the solution of this x, that is phi xx, phi xy, phi yy does not exist. If it is discontinuous, then we can interpret it in certain way, either solution does not exist or infinite number of solutions exist. That is, if you have a discontinuity of a variable across a line, so you may interpret that solution does not exist because the variable is discontinuous, or it may undergo a transition through infinite number of possible values, no matter in whatever way you interpret. Let us try to interpret it in the way that solution does not exist. So, let us try to see an analogy of this with an algebraic equation, so that our understanding will be clear. Let us say that we have two algebraic equations, x plus y equal to 2 and 2x plus 2y equal to 5. So, what will be the nature of the solution of these? Solution will not exist, right. So, how can we assess that the solution does not exist in a more formal way? Here of course by visual inspection we can do that, but this visual inspection gives us a clue. What kind of clue? If we write it in a matrix form, we can see that this determinant is equal to 0. This determinant is equal to 0, which essentially stems from the fact that you have this row that can be written as some linear multiplier of this particular row. So, the second row is a linear multiplier of the first row. So, it is essentially the same coefficient just multiplied by a fixed parameter, and then you can sort of write this matrix in terms of rows where two rows are identical with a multiplying factor, and then that means the determinant will be 0. Of course, you can generalize it to a system of equations with n equations and n unknowns. So, how can we borrow this knowledge from here to here? How can we do that? So, here we want that solutions, we want to get the locus of those points across which you will have discontinuities in phi xx, phi xy and phi yy. That means the solution will not exist, and that is possible only if this determinant is 0. So, for phi xx, phi y, phi xy, phi yy to be discontinuous, you must have this determinant to be equal to 0. So, let us expand that determinant and see that what is the corresponding condition. One important and interesting thing you can see from here is that it is the highest order derivative in the equation that is mattering. So, you have only a, b, c these coefficients appearing in the condition, but not d, e, f, g like that. So, coefficients of lower order derivatives, those do not matter in terms of the characteristics of the equation, only the coefficients of the highest order derivatives, they do matter. So, if we simplify this, So, we can organize the equation in the form of a quadratic equation in dy dx. So, from here you can get the solution how many real characteristics of these will exist? It depends on whether b square minus 4ac is greater than equal to 0 or less than equal to or less than 0. So, just like a quadratic equation, here also this discriminant is what that is mattering. So, there can be certain special cases. So, if you have b square minus 4ac is equal to 0, then how many real characteristics will be there? Only one real characteristic will be there, because this will have only one root, dy dx will be something, so y will be some function of x, only one solution will come out of it. So, this implies one real characteristic. Such an equation is called as a parabolic partial differential equation. So, a parabolic second order partial differential equation will have only one real characteristic. Then if you have b square minus 4ac less than 0, then there is no real characteristic. So, this is called as an elliptic partial differential equation. And b square minus 4ac greater than 0 will have two real characteristics. This is known as a hyperbolic partial differential equation. Remember, this classification is only for second order partial differential equation. So, do not try to generalize it for higher orders, because we are mostly confined up to second order partial differential equations in the context of computational fluid dynamics. So, this is very much pertinent for our discussion. Let us take some examples. What we will try to do is very intentionally, what I am trying to do is, we are first trying to understand these things in a mathematical manner. Next, what we will try to do is, we will try to understand each and every aspect of these equations from a physical perspective, and try to understand that how the mathematical characteristic of a partial differential equation reflects the corresponding physics. How does the physics come out from mathematics? That is what is very important, but first we should learn it mathematically and then try to relate that with the corresponding physics through certain examples. So, we stop here today and we will continue with this in the next class. Thank you.